start the recording before I forget. We don't want to have to construct the volume, or I'm sorry, construct the parallelepiped in order to find the volume. We want to be able to just come up with that volume forthwith. So what I'm going to do is I'm going to create my triple scalar product. Right? So we're looking at, let's get the pen tool going here. So U, a little thicker if I can. Maybe a point, do like a 0.7 for those keeping score at home. And maybe 0.75. All right, so U dot V crossed with W. All right. Now, this is the magnitude of that quantity, but the interpretation here is that it's an absolute value. Right? So we're looking for the volume equal to that. Right? So the setup tells us that we are looking for, use my line draw tool here. So -1, -2, +1, 4, 3, 2, and 0, -5, -2. All right. Now, it is important to note that you have to be dealing with 3 vectors that make up adjacent sides of the corner of a parallelepiped. But you know that's the assumption here, because it says it flat out in the problem. It's more of a statement of fact than an assumption. But generally speaking, if I give you 3 vectors, it's not going to be a trick question. It's a matter of saying, oh, this is what it is. These are the vectors that make up the corner of a parallelepiped. So it's just a matter of putting it into our Desmos calculator, the gift that is Desmos. So I pop in my matrix, hit enter to lock it in, and then I'm just looking for the determinant of that matrix A. And it tells us that we're looking at a determinant of 40. And I'll close it up just to make it look the part. So what we're getting here, so this is kind of weird to think about it, but this determinant is giving us the triple scalar product, which in turn it's a volume. So we need to drop the negative. So we're looking for the volume being the absolute value. I was going to highlight it, but then I realized I'd be pretty much highlighting everything. So I kind of dropped that idea. So V would be equal to the absolute value of -40. So 40 is volume, so cubic units. All right. So that was the first question. The second one, number 11, asked us to show that these points are coplanar. All right. I'm sorry, these vectors are coplanar. All right. So if you know what coplanar means, then you're kind of ahead of the game. You're, well, more than ahead of the game. You're sort of done before you start, because just get rid of this. It's not in the way. We have our 3 vectors that if we go and we're making the assumption that we're looking for a volume here, otherwise triple scalar product wouldn't seem to be the most appropriate strategy. So I'm going to snag some of my work here. You know, I'm not going to be able to take too much of it, but we have some of it. If they're coplanar, then the 3 vectors will contain no volume. All right, so we're looking for 0 volume, right? Because if they're all on the same plane, then that would be the one condition where you would not be able to get a parallelepiped out of it, or at least it would be a parallelepiped with no height, making it a parallelogram, right? At best. You know, at worst, it would be 3 vectors just going off into space, right? Maybe one of them would be in the subspace of the others, but that would be about it, right? So we're looking at 205, 2, 2, 4, and 1, negative 1, 3. All right, so I'll pop in a new matrix. I'll use matrix B, edit, so 2, 0, 5. 2, 2, 4, 1, negative 1, 3. All right, so determinant would be of matrix B, and you can see here that we get a result of 0. All right, so this gives a result, a determinant 0, which means that the volume, I guess I could live with that and shade it in, but I guess I can't live with that. All right, so let me clean it up. 0. So the volume would be equal to 0 cubic units, which means that this is, well, it's not really going to be a three-dimensional figure, which means that they're all living on the same plane. So therefore, U, V, and W are all on the same plane. Ergo, coplanar. All right. So that takes care of page 34, the remaining problems there. You see that they're not too bad. You know, it's in terms of the amount of work that you have to do, it's kind of, hopefully, I guess, maybe the sort of problems, dare I say, you might look forward to seeing on a test. You know, that's probably a good thing. You know, anytime you're looking forward to a problem being on a test, that's definitely a good thing. I'm not big on throwing out hints. I mean, I do it, and then what happens? I mean, you're starting to get a sense of my personality a little bit. We run the risk that I forget what hints I threw out there. I'll give the breakdown of what's exactly going to be on the test as we get closer. And we're getting closer. But what I can tell you is that in previous years, a problem like number 10 or 11 has always been on the second unit test, right? So it's always been there, right? Hopefully I'm not lying about that, but that's what my memory is telling me, right? So just file it away as something, like I said, that you can look forward to. I figure this stuff can be tricky enough without me going out of my way to try to make it trickier. So, you know, I try to avoid the trick questions. That's not to say that there isn't a trick to a question. What I mean by that is sometimes you'll look at a question and think, whoa, this looks like a nightmare, but there's a shortcut through the maze. You know, and if you can find that shortcut through the maze, then you can save yourself some time. So more on that later. I'll show you some little nifty tricks that'll save you some time and energy. I have shown you some when it comes to the matrix stuff, but there's more to come. Exciting times there. All right, so the example at the bottom of page 36 is the line through these points parallel to the line through those points. All right, so well, we can't just go by whether or not they intersect. Okay, so that's good news, because you see the work. I mean, I'm just kind of zooming out, looking at number 5, all that work that went into coming up with that solution may not be relevant here, right? Because what I'll do is I'll come up with the parallel vectors, maybe even the full-blown parametrics for each one, and then see where that takes me, right? Because there's always I call it stopping and looking around. You take a step, stop and look around, see where that got you, right? I mean, if you're taking like the train to a destination, you don't want to have to get off at every stop, look around to realize that you're not at your destination yet. But with the math problem, that's kind of exactly what you want to do, right? So we have our first coordinate that I'll call PO, and our second coordinate that we'll call P1. So our parallel vector would have to be a scalar multiple of the displacement vector between PO and P1. All right, so -2 minus -4. I'll write the steps. Just this once. Because we're starting off class, we don't have a full head of steam going yet, myself included. So 0 minus -6, -3 minus 1. So beep, beep, that's going to give me a 2. An additional beep, beep, incomplete beep. So let me beep it again. Yeah, that gives me a 6. And then no beeps in the last one, so -4. All right, so that's my displacement vector between P sub O, P sub 1. All right, now I have other points. I've already used P sub O, P sub 1. I could use them again, I guess, call it primes, or I can graduate to a different letter, maybe use Q if I want. You got options. Notation is really kind of yours to play with. It's just a question of consistency. All right, so just whatever you call it, don't call it PO and P1 because we already used that, and don't use something. Don't use a variable that you're going to use for something else later on in the same problem. Right? So I'll use primes. All right, so P sub O prime, and this is the geometry prime, not the derivative prime. Right? And you might actually note, if you reflect back on the course thus far, you might realize that I don't use primes for derivatives. Right? And there's a reason for that, because there's such an intersection of geometry and other types of mathematics in this course, but specifically geometry and the calculus, that we do need some geometry notation in order to make some sense of this. Right, so just for consistency, I like to use the primes in the geometry set, like a transformation, that kind of prime. Like if you were to reflect something, reflect point P and it becomes another point, then we would call that P prime. So I'm using it in the geometry context. Fun fact of the day. So I'll just kind of cut to the chase here. -5, -15, and 10. All right. So when I'm looking at these two sets of displacement vectors, what I would want to be making a determination of is whether or not, well, if they're going to be parallel, one would have to be either a multiple of the other, or they're both multiples of some other root vector. All right. So what we can actually do is find essentially, if you're thinking in terms of GCFs, that's really what's going on here. If that's where your instincts took you, then those were good instincts, right? So I would look for a GCF here and factor out a scalar, because if the resulting vectors are the same, then I know what, then I'm there, all right? Then I have two vectors that are parallel to the same vector, all right? So I can pull out a 2 here. I think hopefully that's pretty obvious. 1, 3, -2. All right, so I pulled out a scalar multiple. Then for this one, it looks like, I could pull out a 5 and see where that goes, but I see that I have 2 terms here, 2 components that are both negative. So let's pull out a -5. Trying to pretend like I don't know where this story ends. Like I've done this problem enough that I know what's going to happen. So I know -5 is a better one to take out, but I'm trying to justify the rationale as if I hadn't seen it before. So 1, 3, -2. All right. So you can see here, hopefully, that these 2 vectors, P sub O, P sub 1, the displacement vector, and the prime version of that, are parallel to the same vector. Therefore, they're parallel to each other. All right. So,
Professor?
Yes.
Why is that a -5 again? I'm sorry.
Because I was looking for a GCF, and so I saw that I had 2 negatives here in my vector, and I said, you know what? to make it as clean as possible, my best bet would probably, instead of taking out a 5 and having 2 negatives in my vector, take out a -5 so I could have 2 positives followed by a negative, just like I have over here.
But you got the -5 from subtracting the 10 minus the 5, right? It does not.
No. GCF, factoring out a GCF.
Yeah, what I'm saying, like the -5 before on the first.
Oh, we're dividing.
Oh, dividing. Okay.
Dividing, yeah. Right.
Thanks.
So I'll just write a little verbal statement here. P sub O, P sub 1, and P sub 1 is not going to be a rigorous proof. P sub 1, misspoke, sorry, P sub O prime, P sub 1 prime are each parallel to vector 1, 3, -2. Therefore, they are parallel to each other. All right, so that's a strategy that you could use. I'm gonna just zoom out a little bit so you can see the whole shebang. That's a strategy that you could use to determine whether two vectors are, two lines are parallel to one another. The only issue there is if they're not parallel to one another, if you got to find an intersection, or if you wanted to determine whether they were skew lines, you know, there's an extra step in there, right? So if they're parallel to one another, it'll come out in this process. But if I was looking for skew lines, just because two lines are not parallel to each other does not mean they're skew lines, right? They have to be not parallel, I can't even talk, not parallel and also not intersecting. So I would have to show through the process similar to number 5 that they don't intersect at all, right? And also are not parallel to one another, right? So it's an extra layer of the process, right? So it would be a combination of those two questions that would give you the skew line approach. And you know what? Now that I think about it, it would probably be nice to have an example of that, which I don't have at the moment. I'm hesitant to make one up because I stumble on like the right answer, you know, like something that works too nicely, as in like intersecting lines when I try to make something that's like ugly. So let me just take a second. I'm going to pause the video. Pause the recording. I can actually resume recording here. This is a good thing to talk about at this point because, you know, maybe this question will be a multiple choice question on a test. You know, so like I am going to ask you to write the equation of a parametric, a linear parametric, but maybe it'll be in the form of which of the following is the equation of the parametric, you know, the parametric equation for these two coordinates, you know, and I'll put something absurd in there, like a trig function. I'll put something wrong, but maybe not as absurd, you know, something that's got a polynomial in it. But then I'll put in a couple of reasonable looking linear ones, and the way it'll play out, just kind of spitballing here, is that you'll be able to eliminate two of the choices off the bat based off the absurdity, and then the other two will be the ones that you brute force it out with. And you know, on the off chance that I forget that, it's on my mind now, but it doesn't mean it'll be on my mind later. I'll take that as a typo too. Somebody send me a message saying, "Don't forget the parametric multiple choice question." I'll know what that means, right? So if you haven't been submitting for typo bonus, because I know a lot of you haven't, a good chunk of you have. My suspicion is that maybe you're not submitting because you don't know that it's an option, right? So anytime I point out a typo in class, or you notice a typo in my handouts or on my website, or any message I send you, anything. Like my whole existence boils down to me trying not to look like a fool. All right. I figure nature already did that. I don't need to add on to that, through my own lack of focus. So what you can, it sounds like people are getting the message, which is good. So what you can do anytime I make a comment saying there's a typo, submit this for a credit, just send me a message on Remind. Remind is the best way to go. Some of you send it on through email. That's perfectly fine. Don't get me wrong. Email is fine. It's time stamped. It's great. The issue that I've kind of discovered is that when you do it on email or through email, you have the layers of, okay, you gotta get the email address in there. And when you write an email, you feel kind of compelled to, include a salutation like, oh, hope you're doing well, that kind of thing. And then you put in the typo. By that point, oftentimes, 30 people have already beaten you, right? So just a thought, doing it on Remind might get it quicker. So, and for typo bonus, my feelings don't get hurt if you dispense with the niceties where you say typo and then just tell me what the typo is, because everything else is timestamped. All right. So there it is. Anyway, I'll put in a curve here. Let's say we want t -1. And let's go, I'll try to keep it relatively simple. T +1, and then, nice 2t. And then let me do, I got to tell what the variable is, and then let me do -10 to 10. It gives my parametrics. All right, so I zoom out substantially just so I can make sure that it's going where I want it to go. All right, so in terms of coming up with another linear function, there's a couple ways you can handle it. One way might be a little bit better than the other. So I want to make sure that my line is not going to be parallel to this one, and it's not going to intersect. I could do a little trial and error, but I could also get a little sassy here and maybe just put in y = mx + b for each component. All right. So the thing is, I'm not going to use x, I'm going to use t, and I'm not necessarily going to use m and b across the board. I'll use different values. So let me say a instead of x, t + b. That's a linear model. All right. So c, t + d, and then e, t + f. All right, so I'm just putting in some constant values of multiples and coefficients, all that stuff. All right, variable t going from -10 to 10. Then when I hit enter, it creates all these sliders. So you can see that the slider is going to have an impact. Oh, it says curve issue. Of course it does. Well, I got my sliders. Oh, I already used A for something. Yeah, A is already used. You can see at the top here, A is used as the name for the curve. So it got confused. All right, so we got to be careful about that. So what I can do is I can call that something else. Let's call it something I'm never going to reference again. Let's call it, I don't think I'm using P. So got that. Then I just need the slider for this. So what I can do is I'll just redo it so I don't have to worry about if I hit duplicate, I want to hit delete. I don't want to have to worry about troubleshooting, when it inevitably doesn't work. So AT + B, comma, CT plus, I hit the subscript E, D, comma, ET plus F, A, B, C, D, E, F. Okay, I haven't used those anywhere else. Should be good. T, -10 to 10. All right, now if you were able to play around with the second technology assignment, again, the video is posted on the YouTube playlist also referenced on Blackboard, so everything you need is there. You'll see that this concept of parametrics and sliders comes into play pretty substantially. So you can see I have these coefficients here. Oh, see, look, here's something else that you got to be mindful of. E is actually Euler's number E. So it's already earmarked for something else. So let me make that G. I know it's going to be out of order, but that's fine. So I'll make it G, and I'll need a slider for that, right? So it's kind of good, I guess, that I'm discovering all of these issues now with you so that you don't have to discover them all later on your own. That's something, right? So let me get rid of that. It's still pulling back the E, so I want that to be G. And then it locks it in. All right, so just make a little tweak, and then there you go. All right, so now I can kind of play around with it. I'll bring it in a little bit so I can see, get an idea. This looks like it's a set of skew lines. Right, they're definitely not parallel to one another. Right, they're a little bit off. But I'm not in love with that 2 as a coefficient. So let me make that, well, that's the G value. So let me make that, I think I said 2, I meant 2.5. So I can slide back and forth to make that something else. Make it a 3. That looks fine. Also, you know, this looks a little bland. So let me spice it up a little bit. Let me make this, I'll shift it over here. I'll make that a 4. Do a little horizontal shift. Yeah, 0. One of them could be 0. There's nothing wrong with that. Now, if you see that it's having trouble locking in, you got the old fat fingers or shaky hands, you could just click on it and change it. That's perfectly fine. But you throw yourself a gimme here. The A and B values, let's make one of them negative. Just click out and then click back in. There we go, and I'll make this, I'll make that a 5. All right, so this is, it seems like it's definitely a set of skew lines. They're not parallel. They don't seem like they're going to intersect, although, oh, actually, maybe they would, I don't know. Well, I guess we're going to find out, right? So that's the beauty of it. All right, so I'm going to jot these 2 parametrics down. Now, the good news is I've already created the parametrics just for fun with GeoGebra, so I don't have to derive them using the actual coordinates. So that's something to keep in mind. All right, so let's call, well, I'll show you my display in a minute. Line L would be t minus 1, t plus 1 and 2t. And line M scrolling. Negative t plus 5 t and 3t plus 4. All right, so let me stop this share. So we know, but it at least appears like they're not going to be parallel or intersecting. Could be wrong. I didn't investigate. I didn't zoom out as far as eternity. You know, it looks like they're just going to miss. You know, it like you have it at the wrong angle. It looks like they'll hit, but it looks like they're just going to miss. You know, 2 planes that, not like literal planes. You know, like airplanes. They're flying. One's going north to south, and one's going west to east. You know, but they're flying at different altitudes. So you know, they're, you know, a top-down view may look like they're going to collide, but they're not, because they're 500 feet apart. You know, or 1,000 feet apart. So let me stop this share. Start this share. All right. And so these would be our parametrics that we're kind of playing around with here. All right. So I would ask, do L and M, poor quality script M, intersect? So we'll start there. All right. So corresponding parts. You could use the matrix approach, but we do have to make an adjustment because again, we can't assume that that they're working in the same universe, that these t values are the same. So what we're going to do is we're going to rewrite it so that it's t minus 1 is equal to negative s plus 5. All right, so we're making the adjustment where each of these t's become s's. All right, that allows for the fact that they're not necessarily, the origination point for each line is not necessarily at the same location. They're not moving at the same rate. They're not using the same number system. Like, for example, one of them could be in inches and the other could be in centimeters. This is allowing for us to come up with values in each system that'll make them congruent, geez, I'm really getting into geometry here, equivalent to one another, but we're not assuming that t means the same thing from one system to another, right? So then t plus 1 would be equal to s. 2t would be equal to 3s plus 4, all right? Now, your choices here would be to solve it algebraically by hand if you want. It wouldn't be too terrible in this case because we already have s solved in terms of t. So if you wanted to do it that way, that would be great, you know, like in this case, but it wouldn't be so great for some of the other problems that we've come across, right? So it just another ism of mine, prepare for the worst and hope for the best, you know? So you go into a test expecting to do it with a matrix approach, but then when you look at it and say, oh, this is easy to do by hand, then you go and do it by hand, all right? So I'm going to add s to both sides, so I have s plus t. And then I'm going to add a 1 to both sides, it's going to be equal to 6. All right. I'm going to subtract a t from both sides, s minus t is equal to 1. All right, so very easy to do this with elimination. All right, so not too bad at all. And then subtract a 2t from both sides, we get 3s minus 2t. Subtract the 4 from both sides, you get a negative 4. All right, strip it down to just the coefficients. So why am I writing a variable? Who knows? 1, 1, 6, 1, negative 1, 1, 3, negative 2, negative 4. All right, and so we're looking to find, oh, it's a matrix, not a determinant. All right, we're going to put this in reduced row echelon form. So new matrix, 3 by 3, 1, 1, 6, 1, negative 1, 1, 3, negative 2, negative 4. All right. So then when I row reduce this with the RREF technique, I get this solution, quote unquote solution. All right. Let me pause the recording and see. I got a couple questions. All right. So we get the identity matrix, which if you're a linear algebra person, you might look at that and say, oh, that's wonderful. The identity matrix is usually what we're aiming for in most cases, but I'll show you why this tells us that there is no intersection between the two lines, right? Because again, the first column represents, and so these are all coefficients, all right? Coefficients of S and T, all right? And then the last one is just constant. All right. So when I rewrite this, this would be saying, if I go row by row, I'd be looking at 1s plus 0t equals 0. There's a little sidebar to that. That would tell us that s is equal to 0. That's possible. All right. But then for the second one, I would get 0s plus 1t equals 0. Also possible that t could just be equal to 0. Although now I'm getting a little suspicious. It's like, well, they can't all be 0. You know, I'm sorry. I don't know why. No, 0. I thought I misspoke there for a second, but I guess I'm becoming so accustomed to misspeaking that I was surprised that I actually said it right. So the last one is where things start to fall off the rails, because we're looking at, or completely fall off the rails. It's not even start. We have 0s plus 0t is equal to 1. That's a contradiction. 0 equals 1. Not true. Contradiction. Which tells us that there is no way that we could have a point or a coordinate that coincides between those two lines, right? So therefore, no intersection. All right, so there's no intersect. So then it's just a question of determining the parallel relationship between these two lines, all right? Now that we could actually have done in the beginning. So, but we needed to figure out whether or not they intersected anyway, because if we're looking for skew lines, the hardest part is determining whether or not they're actually intersecting. So we might as well get that out of the way first, right? Although you could save yourself the time and say, well, they're parallel, so therefore they're not skewed. So you go down that road first and all of a sudden you're fine. But it is kind of frustrating when you go looking for whether or not two lines are parallel, and then you find out that they're not, and you say, okay, well, now I got to do the other thing. You're like, dang it. It's kind of like, I always kind of go back to trig. And my trig analogy here is, it's like law of sines, law of cosines. Nobody likes performing the law of cosines. It's just tedious. Law of sines is, okay, it's tedious too, but it's less work. So you kind of go into a problem hoping it's law of sines, but then you're like, ah, crap, it's law of cosines. In algebra, it's like, oh, maybe it's a factorable quadratic. Ah, crap, it's quadratic formula completing the square. It's the same idea here. So what I would do is I would take, again, my lines. So let me bring them back. Now here I can just actually leave them in their current form without having to worry about the essence. I lost it there for a second. So what we would want is the parallel vectors. If you know the model, for a lines in a parametric form, then you're in good shape. So you got your XO plus TA, you got your YO plus TB, and your ZO plus TC. All right. So whatever the coefficient is of T is going to be the parallel vector, or at least a multiple of the parallel vector. All right. So what I'd be looking for here is the coefficients of t, in this case 1, 1, 2, and in the case of m, -1, 1, 3. All right, so either they're going to be multiples of one another or multiples of some other common vector, right? There's no GCF for L, and the best you could do to pull out a GCF for M would be to pull out a -1. Either way, you're not getting a common vector. So no GCF will give a common vector. Therefore, not parallel. And so our final conclusion for this problem, which is the worst case scenario when you think about it, because all this work had to happen, although a lot of it happened behind the scenes. I mean, it could have been worse. You know, the calculator did at least the algebra part for you. So conclusion, and I'll do that in green for those keeping score at home. Conclusion, L and M are skew. All right, so they're skew lines. All right, yeah, so not only do I need to get this into future notes, but I also need to, it looks like, give like at least half a page of space in order to complete it, maybe even a full page. But this will be saved in your notes. These class notebooks, as you know, are always available online in this form. I just put it at the end of the note packet. I'll move it into the proper placement later on. I'm not going to do it. I'm kind of thinking about whether or not I should do it now. Yeah, I should do it now. So what I'll do is I'll stop the recording